Hello, everyone. In this discussion, we are going to talk about the precision analog signal acquisition systems. Okay. And before we start about the technical discussion and how we can design such a system, let's talk about why we actually need the precision analog signal acquisition system. Okay. Now, normally, when we work with any type of system, okay, our input signal, which is the input of any type of processing system or control system, is going to be the output of some sort of sensors. Okay, those outputs are normally very low voltage or current signals, and they are very vulnerable to the noises and electromagnetic interferences. Okay, we need to deal with the shortcoming of and problems in those signals. So we make sure that our processing system, okay, that's gonna deal with that input signal, so it could get us what we need at the output, would be able to like run properly, because it doesn't matter how good your system is. Okay, if you have a bad input, you are going to get a bad output. If you have a faulty, noisy input, you are going to get a faulty, noisy output unless you address those problems. Now, normally, the output of sensors are very weak signals. Okay, so the values are very low, which would create problem when we talk about like a signal to noise ratio. Okay, and even in some cases, some of the analog devices like op amps that we are working with, or the transistors that we are working with, they are not going to be able to like detect, follow, or even activate based on those signals. Okay, based on the values of those signals. And basically, it makes those devices move away from the linear behavior and go into the saturation or nonlinear behaviors. Okay, so then we don't have a proper control over our system. Now, this is one problem. So, how we can solve it? We need to amplify our signal. Normally, the signals from the sensors are noisy because there's a lot of interference, electromagnetic interference in our environment, most specifically high frequency noises. Okay, so this is another shortcoming or pitfall of those signals that come from that sensors. We need to deal with that noise, meaning we need to filter those noise out. So another problem that we have to address in those signals is high frequency noises. Now, all our devices normally work based with supplying from a power line. Okay, so without that power supply, system would not get energized, system would not work. So we need power line. Okay, now, although power line is necessary, but it would have a negative effect too. We are working in a world of electromagnetic fields and waves. Okay, so power line would also have an electromagnetic interferences on our device. The power system works in like a 60 hertz. Okay, so we are gonna see interference at that frequency in our system. We have to also filter that specific interference out of our signal. Now that we know what are the problems and what kind of what are those problems that we have to answer, let's see how we could design our precision analog signal acquisition. Now, always the first step of the design, always, doesn't matter what you design, okay, is to simply draw the block diagram of what you need in order to start with the input, okay, and basically check mark all the goals you have and receive the desired output. Now, 1, 2, 3, 4, we are going to address these stuff. So we have our input, okay. The first problem that we needed to address was the input was weak signal. So we need to amplify that. So we need an amplifier in our first part of our system. So the first part is an amplifier. After amplifier, okay, we need to address the second problem. We have high frequency noise. How we can deal with those? By adding a low pass filter. Now this part addresses the second problem. Now, again, we have problem with the power frequency interferences, which is the 60 hertz, okay? 60 hertz frequency. Now, we need to eliminate that 60 hertz frequency. So we need to have a band pass filter, which filter out the frequency around that desired, that targeted frequency, that 60 hertz frequency, okay, and let the other frequency pass through without any attenuation. How we can do that? We can implement a notch filter. So now we have a notch filter in our system in order to address the third problem. When we address all those problems, now we have our desired output. Now, we know based on this general structure, now we know what we need. So in the next step, we are gonna focus on each of those blocks, and we are gonna design the circuit that are gonna basically perform what that block, what each specific block needs to do. Okay, so in the next part, we are going to focus on amplifier, and we are going to design a specific amplifier, talk about a specific amplifier that would deal with that weakness of our input signal. Okay, now let's focus on the first block, which was our amplifier. Okay, the most popular and easy to design circuit for amplifying in a precision analog signal, okay, is the 3-op-amp amplifier. What it does is, first of all, it amplifies a big signal, okay, and since in 3-op-amp amplifier we have a comparator op-amp, okay, which tries to identify the difference between the two inputs. Okay, basically, if we have, but because of that characteristics, if we have any common noise in those two inputs, that comparator would cancel those common noises out. So it's a little bit actually help to purify our signal, but we don't focus on that. It is like a bonus on that circuit. Okay, what we are going to focus is the amplification of that 3-op-amp amplifier. Now, here you can see the circuit of the 3-op-amp amplifier. We have our input, that faulty, weak, noisy signal. The 3-op-amp amplifier has 3-op-amp is in the name. The first stage of the circuit is the op-amp 1 and 2, which works as a buffer to isolate the input from the rest of the circuit. This is the first block. The second block is the gain of the circuit. So this block defines how much you amplifies your weak input signal So you have a measurable, proper output signal. So this is the gain of your 3-op-amp amplifier. And the third one is that the comparator that we talked about. Okay, now comparator, this block would have a certain gain too. We normally do not count on the gain of comparator for amplification for the whole circuit. So we normally set the comparator as a unity gain. How we can do that? If you go through the theory, the gain of such a comparator, the gain of such a comparator is going to be, the gain is going to be R2 over R1. So if we put R2 equal to R1, that means the gain here is 1. So we don't amplify anything in a comparator. It's a simple comparator, unity gain. Now, let's kind of like talk about what's going to happen to our signal when we have such a circuit. Now, I put one input. You can have two separate inputs for the buffers, but because I want to like talk about the sensors and how we can basically pre-process the output of the sensors for our system, I put only one input source, which the two terminal of the input would get injected to the two buffer. Okay, now the input will be injected to the non-inverting port of the buffer op-amps. Okay, both op-amps. So please pay attention. The both terminal of input are connected to the non-inverting ports of our op-amps. Now, let's mention the name of the nodes in here so we can analyze the circuit. This is the op-amp 1 non-inverting voltage. Let's recall it V1 positive. This is the V1 inverting. This one is V2 inverting. And this one is going to be V2 non-inverting. Okay. We are going to call the output of the first op-amp as V1. And the output of the second op-amp is going to be V2. And the whole output, it is obvious, it's going to be V output. Eventually, we are going to see what is the ratio, because this is amplified. What is the ratio between V output versus V input? So what eventually we care is the gain, which is that V out over V in. Now, I wanted to make it easier a little bit. Okay, and since this is a signal, like an alternative signal, so there is no positive, negative terminal, I'm going to connect this part of my input to the ground. So this is 0, this is V in. Okay, this is V in, this is ground. This is for simplification. You can kind of like eliminate this assumption. Now, let's see what's happening in this circuit. If this is ground, that means non-inverting V1 plus is 0. Let's write it down. V1 plus is 0. Now, we have an op-amp. Between the two ports of the op-amp, between the inverting and non-inverting, we have a very high impedance, ideally infinite. Okay, what that means? That means there is no current passing between the two terminals. What that means, if you have no current, there is no voltage drop between the two. So if this is 0, the inverting voltage is also 0. Therefore, the V1 inverting, V1 minus is also 0. Let's put the units too. Okay, now how about this one? V2 non-inverting, V2 plus is our input. Same analogy, because we have an infinite impedance, high impedance, ideally infinite, or there is no current, there is no voltage drop, so V2 inverting is also equal to V input. Okay. Now, let's see what's happening here. In our gain stage, we can apply Ohm law in all these resistors. And since these current, there is no current injecting or coming out from the ports, the input ports of the op-amp, so we don't have any current here. This is 0, and here. So whatever current passes through RF, same current goes through RG, and same currents go through the second RF. These two normally are equal to each other. That's why I named them simpler. Okay, so all the current through these three are going to be the same because we don't drain any current toward or inject any current from the op-amp's inputs to these two nodes. Okay, so let's do the Ohm law for each three resistor. For the first one, we have V1 at the one side of the resistor and V1 minus at the other side. Okay, so consider the current is that way because we have the positive, this is the ground, we have the positive here, current that way. The Ohm law says V1 minus V1 inverting, that's better, minus V1 over RF is going to be the current here. And it's equal to the current over RG. What is the current over RG, passing through RG? It's V2 inverting minus V1 inverting over RG. Same goes for the second RF, which means it's V2 minus V2 inverting over RF. Now we have our three this one, V1 inverting, we already know it's 0. So this is 0. Okay. V2 inverting is V1, yeah. So this is also 0. V2 inverting is V in. So this is input. Here also, this is input. Are we good? Okay, so let's kind of like figure out what is going to be V1, how we can identify V1 based on V in, and how can we identify V2 based on V in. Okay, now, where should let me eliminate this part so I can follow the rest of the analysis. Now, if you look at this part, okay, V1, okay, is minus, I'm just changing this, minus RF over RG times input. Okay, which makes sense. We already know that. We expected that. How about V2? Let's talk about this part. V2 is equal to, we have to multiply everything by RF. So here we have it becomes RF times V in. This is 0, we don't care. So this will be gone. Now we have V2 minus V in, we transfer V in to the other side of the equation. So it's going to be 1 plus RF over RG times V in. Okay, are we good? So far, we find V1 and V2 based on input. Now, let's move to the next stage of our 3-op-amp amplifier. We have a unity gain here. That means R1 and R2 would not affect basically the signal. So the output of this comparator, let me use another color. The output of the comparator would be simply the difference of V3, no, not V3, the difference of the input here, the non-inverting input, which is V2, minus the inverting input, which is V1. Okay, there is no gain because we set it as a unity. If we don't set these R1 and R2 equal to each other, there are going to be a gain here. There is going to be a coefficient here. Okay, now let's put in everything. So now V out is going to be equal to V2 was 1 plus RF over RG, okay, times V in minus, which we have minus here, become plus RF over RG V in. So you can easily see that the gain become 1 plus 2RF over RG times V in. Okay, so this is our gain. This part is the gain of our 3-op-amp amplifier, considering the comparator is a unity. If not, we have, if we don't set that as a unity gain, here we are going to have times R2 over R1. But since we set it as a unity gain, so we don't have this. Now, what that means? That means here, by changing the RF or RG, we can change the gain and adjust the gain. Now, we have 2 RF, so it doesn't make sense to change both of them, and probably we cannot adjust them exactly equal. So it's better to use the RG1 resistor to control the whole gain of the system. That's why I put a potentiometer RG. So now by changing the RG, we're changing the denominator. Ergo, we're changing the whole system. Now, I'm not going to mention any numbers, okay, for RF and RG or R1 or R2, okay? It's your job, okay, to design that. Now, but this is the general description of the 3-op-amp amplifier. Now, let's go to the lab and see if this circuit actually works as it was intended. Okay, now that we talked about the theory behind the 3-op-amp amplifier and how we can design it, how we can tune the gain of amplification that we want, let's look at the text experiment and see how it works. Okay, now you won't probably kind of like be able to like recognize what's what in the circuit that I implemented. Is a very crazy kind of like schematic when you want to apply it on the circuit, but let me explain that. I have two op-amps, two op-amp IC. What I mean the two op-amp IC. One is the LM324, which we know it has 4 op-amp in it. I am going to use the 2 of those op-amps for the buffer op-amps that I had, like A1 and A2 in the theoretical discussion. And I'm going to use a comparator op-amp, 329, which give me the ability to have the third op amp in my schematic as a comparator. Now, I already connected the VCC to all the op amps, connected the non-inverting ports to the input signal, to the both side of the input signal, and I put the inverting part as the feedbacks that we had through the gain structure, that gain block that we have to RF to the feedback resistance, and that ground resistance are using a potentiometer for that RG that we talked about. Then the output of those two op amp is going to be the input of the comparator op amp, which is also connected to its own VCC and ground. Now, pay attention. I said its own. That means you have to have two separate sources, DC sources, to supply the two op amp. Otherwise, your DC source cannot properly supply the two op amp. And basically, the voltage and the current changes from the ideal setting in your DC source. If you supply the two op amp from one DC source, they would affect each other. So you won't get a proper result if you do not separate those VCC and ground system. One micro VCC of comparator is disconnected. Let me fix that. Come on. Grab it. Okay. Now, there are several points that you need to know. You know that the op amp only works if the voltage is positive. So when you input the signal, you need to have an offset. So we make sure that when our sinusoidal changing, we won't go to the negative values. We don't cross the zero line. So you need an offset. I'm a little bit too conservative, so I put the 6-volt offset on the signal that I have, and my signal is 1 volt peak to peak. Now, in reality, you don't have the setting for offset when you work with the sensor, so you need a pull-up kind of like circuit to add a certain value of DC, so you make sure that the input signal would never cross the zero line. Now, since we have a comparator in our circuit, and basically in the gain block, also the two op amps, the two buffers, input and output are affecting each other, we need to make sure that the non-inverting port of the second op amp and the non-inverting point of the first op amp, okay, are gonna be at the same level. Now, in my design, I had one signal as an input. I grounded one of the inputs of the op amps. Okay, so one side of the AC signal, that AC source, I connected to the ground, so it's 0, and the other side would float based on the function of that signal. Okay, now you cannot connect directly to the ground. That's what I'm saying. Because you have an offset of 6 volt, for example, in this setup, you need to also have an offset of 6 volt, okay, DC, in the other input. So instead of grounding directly and making it 0, okay, I put the non-inverting input of my other amplifier, the one that doesn't have the variation signal, the variating signal. I put that in a 6 volts. So we have the same amount of voltage level. The only difference is gonna be, because it's a comparator, okay? The only difference is gonna be the variation in a sinusoidal. Okay, now You can see my output. Let me set it again. My channel 1, the yellow one, is my input. I am gonna change the value of the voltage division so it would be more clear how the gain works. Okay. The input occupies one a square in our grid, and the voltage is 1 volt, which I expected that because I said that is a 1 volt peak to peak. Now, my voltage division in my second channel, the blue one, is also 1 volt. Okay, but you can see it's almost 1.8, close to 2 volt of peak to peak. So you can see that we have 2.8 amplification in the output in regarding the input. Now, if I change the RG, you can already see that my gain is changing. So right now, my gain is 1.4. Okay, now let me go another way. Okay, I can't go very far because then my op amps get saturated. I'm passing the limitation of the output of the op amp, so I'm going to the nonlinear. So this is what's happening here. But this is the margin that I could go. This is the highest that I could go. And you can see what happened. Oh, disconnect. And now you can see is 2 volts. So my first one was 1.8, the gain. The second one, when I changed that, it was 1.4, the gain of my amplification. And now I have 2 in the as the gain of my amplification. So by changing that potentiometer, I can change basically my gain. Now, this is my design, so I put a specific resistance. Okay, I try to, based on our discussion, to have a unity gain in my comparator. It's not going to happen in reality because those resistors has errors, so it's never going to be the same value. So you're never going to get the unity gain in your comparator, but close enough. Okay, so my comparator would not change the gain, and the values that I have for the gain block, I set it to get like 2.5 gain as a gain. Now, I have a restriction in my kind of like resources, so I can't go to actually 2.5. You saw that it would go to the saturation part of the op amp, so that's the limitation I have, but so far it's good. So I can't reach the gain of 2. You can change the gain based on your own design, play with those values of RF and RG, and you can have the gain, remember, is 1 plus 2 RF over RG. Okay, so this is the gain. And you can design your own. Now, let's move on to our low pass filter. Okay, the second block that we had was the low pass filter. Okay, we wanted to like design a filter, a low pass filter. Okay, so we could eliminate all the high frequency noises. Okay, it is very easy to actually. I assume you have a very good knowledge by this at this time to actually create a filter, and we actually had already covered how we could design an active filter. Okay, you remember this circuit? We already have that in the lab 3, okay, when we talked about the op amps. So I'm not going to talk about the active one. We already talked about it. I am going to talk about the passive filter, which, by the way, for our purposes, for these purposes, that's enough. You know what I'm saying? Because it's the active filter is just extra cost, you know. And we are engineer, we care about money. So now This is a simple low-pass filter. We have an RC circuit. This is the first order. You can have a second order, but first order is good enough for these purposes. We have a first order RC low-pass filter. When we inject the input into our circuit, and the output is going to be the voltage across the capacitor. Okay, now what's going to happen? If the frequency increases, the impedance of this capacitor would decrease. We know that the impedance of the capacitor is the Z is 1 over J omega C. So if the omega increases, impedance decreases. What that means? That means you eventually, if it limits to infinity, you have a short circuit to the ground. So the signals with higher frequency prefer to go to the lower impedance. This is a current division rather than the rest of the circuit. Now in lower frequency, this is happening in higher frequency. So it goes to the ground. In lower frequency, this is a notable amount of impedance. So we are going to have a normal current division. Like when we talk about like frequency near zero, this is actually the impedance become infinite. So we actually don't have any current passing to the ground. Everything is going to be going toward the output. So, you know, this would help us to have a low pass filter. It's not going to be exactly zero, so let's be precise. And this is the cutoff frequency. Okay, so this is how it works. This is the gain of our filter, and this is going to be the frequency of our circuit. Now, how we could design that is very simple. The cutoff frequency, which is the desired margin that we want. So, for example, we could say, I want everything after 100 hertz to be eliminated or attenuated. So we set the cutoff frequency at 100 hertz. You could set that in your desired value. Okay, this is an example. Now, if we set the F of cutoff in a certain value, the relation between the cutoff frequency and values of R and C is the cutoff frequency is equal to 1 over 2 pi RC. Okay, so whatever cutoff frequency you have, you can have the values of RC. Now, normally you have to assume or like set one of these values and then find the other one based on that value. Normally we set the resistor. So for example, if you set the resistor in like, let's say 1 kilo ohm, okay, now you can calculate the C based on this equation, which is going to be the 2 pi R F of C. And this way, you can calculate what kind of capacitance you need for this resistor, so you have a cutoff frequency of your desired value. So that is, okay. And you already know how, if you want to like use an active filter, okay, which would have a strong output, but as I said, it is costly, and then you have like provide a VCC because you're using an op amp and you have to basically supply energy for those active devices. You can use our discussion in previous lab in order to design the active filter if you want. Okay, so let's go to the lab and implement this RC first order low pass filter and see if it works or not. Okay. Right now, I created my passive low pass filter. It's a simple RC filter. We already talked about that.
For the input, I use the output of my three op-amp amplifiers. Okay, and the output of this filter is going to be the voltage across the capacitor. Now, right now I have that 1 volt peak to peak with a 6 volt DC offset that we had before, and I set the frequency at 50 hertz. Okay, my gain is right now 4, my gain of amplification. So it took that 1 volt signal. My blue line is the output of the amplifier. So the voltage division is 2, so it occupies 2 units. So it's 4 volt. So right now I changed it a little bit, the circuit. So right now my gain of amplifier is 4, okay? And the purple one is the output of my low pass filter. Now I am in 50 hertz. I set my cutoff frequency at 100 hertz, okay? So I'm 50 hertz, so I'm below the cutoff frequency, and you can see the gain is 1. So again, the voltage division for my third channel, the purple one, is also 2 volt, and it occupies 2 units, so it's 4. So not now in 50 hertz, it doesn't change at all. It doesn't attenuate the signal at all. Now I'm gonna change the value of the frequency, so I'm going to the 80 hertz. And now you can see it's a little bit of change. I hope you can recognize that. It's a little bit of change. So it is slight attenuating. I'm going to the 100 hertz. Now I think is more visible. You can see, hopefully it's close enough. You can see that this is getting smaller and smaller. Okay, now I'm going to the 200 hertz. See, it get attenuated. My input and output of the amplifier doesn't change, but my output of the low pass filter is changing. So I am going to let's say 1 kilohertz, and see it's completely attenuated. So it's gone. Okay, so my low pass filter works properly, and then my design the design that we had actually was correct, and we are going to get the same result as we expected. Now let's go toward the notch filter.
Okay, now let's talk about the third block that we had in order to eliminate the power line interferences that we could have, that 60 hertz EMI that we might have in our signals. We said we could use a filter, the band pass filter, specifically a notch filter, okay? So we can eliminate that specific range of frequency. Now, in this part, I am going to talk about a notch filter, more specifically a passive notch filter, okay? You can see the circuit for a passive notch filter, okay, which is basically the combination of a low pass and high pass. We have our input, we have our low pass, and we have our high pass filter, and then we have our output. Okay, now how to design this is very simple. You can see that the simple structure of the notch filter, the passive notch filter, is in a way that basically you can use the relation between the capacitors in order to simplify the formula for the cutoff frequency. I'm not gonna bother you to go through all the mathematical derivation. If you choose this resistance as R and choose the low pass part of the filter as 2R, 2 times that R, use C as a capacitance in high pass and use 2 times C in the low pass. So basically the values in low pass are twice the values in high pass. Okay, then you can simplify the formula of the cutoff frequency to again 1 over 2 pi RC. And then you could estimate, you know, what is the desired FC. Your cutoff frequency should be 60 hertz. You want to like cancel out the power line frequency. Okay. You can imagine or like assume a specific kind of like resistance, like for example 1K, and then use the formula to calculate your C, the value of the capacitor. Okay, you can choose other resistance value too. Basically, it would change the capacitor, but since we are working with a power line frequency, set the cutoff frequency for the passive circuit at 60 hertz, so you have a proper kind of like gain for your filter. Okay, and you are gonna see such a behavior. So we have no attenuation in a low frequency, and then near that cutoff frequency, like this is the cutoff frequency, we are gonna see some attenuation, and then again the filter would allow the higher frequency to pass. So this is gonna be the performance of a notch filter. Okay, now let's move on to the active notch filter. Okay, now let's talk about the notch filter, specifically active notch filter. Okay, the circuit that you see is the active notch filter. Okay, it has two main parts, two initial parts. One act as a low pass filter. You already know how to design that individually, and another one is a high pass filter. Okay, you didn't still design such a filter, but it's the same. Theory is the same. Okay. The other part is a gain value. So we have a system, we have a low pass, high pass system. This part is just amplify whatever is at the output of our notch filter. And the value of amplification, you already know this is a non-inverting amplifier. So the value of amplification when these two are equal is basically the gain is going to be 1 over 2. Okay, so whatever input we have, half of that would be in output. Okay, now let's see how we can design such a filter. These R's are not going to affect the performance of a notch filter. It only affects the gains. So I suggest you to put all of them equal to each other. Okay, now you don't want to like focus on that because what we want is the performance of a notch filter. So what is important is these RC and these CRC. In order to have a notch filter, when you have two low pass and high pass filter, you need to actually define the band that you wanted to like cut out. We said we wanted to like cut the 60 hertz frequency. So let's define the minimum cutout as 50 hertz and do anything else. And the max cutout as 70 hertz. Now, basically, we can set the low pass filter with the minimum cutout. So this goes to the low pass filter. And we can set the high pass filter with the maximum cutout. That way, this one allows frequencies lower than 50 to pass, and this one allows frequency higher than 70 to pass, and eventually you have lower than 50, higher than 70, and you cut out what's in between, which is the aim of our notch filter. Now, how can you design each of them? Again, simple like the other filter that we designed, the low pass filter that we designed, the frequency, the cutoff frequency is 1 over 2 pi RC. For the first one, you have the formula. Frequency is going to be 50 hertz. You assume 1R, one value for R, and you calculate the C for the low pass filter. Then you put the frequency, the cutoff frequency equal to the max for the high pass, 70 hertz. You assume a value for R, and then you find the C2 for the high pass filter. That way, it's already designed. Very simple. Now, we can go to the lab and see if actually this circuit works. Again, I'm not going to give you the values. Okay, it's your job to design that, but this is how we can do it.
Okay, now I added my notch filter to my circuit. The purple one is the output of the low pass filter. The dark blue one is the output of the notch filter. Okay, now I set my frequency at 50 hertz. I expect the notch filter to attenuate that, so you can see it attenuated. Let's go to the 60 hertz and see, because that was my goal, my desired frequency. You see that in 60 hertz, the attenuation get better, so it attenuate the signal better. And if I go, for example, in like 10 hertz, okay, now as I expected, my low pass filter created a better kind of like gain, more flat, equal to 1 gain, because it's far from the cutoff frequency for my low pass. And you can already see that my notch filter also have quite a good gain. Okay, so it allows that 10 hertz to pass properly. So my notch filter is also working. So this is what I expected at 10 hertz. So we have the gain that we want. The low pass filter works properly, the notch filter works properly, and now we had an amplified version of our weak signal that we had. So this is how the instrumentation amplifier works, and how we can design and test the amplifier.